and we are going to get into kind of the details of our frequency lab. So we have some fundamental equations, again, that we kind of made these some assumptions last time. So massless beam, not really, because it is not massless. Rigid, not elastic, it is elastic. And then we also placed this additional mass on our beam, the accelerometer, and the accelerometer has some mass. So all these things are going to basically affect our experimental measured resonant or dominant frequency. And then we also have to calculate if that overlaps with our, so there might be some difference between your experimental frequency and your theoretical frequency calculated below. So we're going to measure that, we're going to see the overlap, and then see how the frequency changes as a function of length. So this is our equation that we deduced last time. So actually I'm going to change this width. Instead I'm going to make it, actually let's just keep it as a width. It's basically your base, but I'm a material scientist. I'm not a mechanical engineer, so I always kind of just keep it as width. But you can kind of see how the expression changes. And height is going to be essentially the thickness of your beam. So here, 2 pi L squared. This is just the same expression that we saw last time in our lab handout here. Again, for a cantilever beam, again, assuming rigid, assuming massless, but again, those are going to be some differences between the real, this is the theoretical equation. We're going to see if it overlaps with the experimental conditions. So how good of an approximation is it, assuming that this bead is rigid and massless, and that's not the case, and we're adding an additional mass to kind of measure these frequencies. Let's see what happens. Young's modulus, inertia, etc., etc. So here, I'm going to plug in, and then now I can kind of see my equation reduces. So right now, I can already start to see, okay, my frequency is a function of my height of my beam, my Young's modulus, the density of my material, and the length. So I have 4 independent variables. So I might want to do df dh derivative, start doing that, h, and then I could also divide that out later, but you might want to start doing this for my theoretical frequency, or my bias error for theoretical. So df dy, function of y, and you could double check here, etc., etc., etc. So you can kind of see where we're going with this. So there's going to be some bias when we're calculating the theoretical frequency. In this lab, you are not given, the only data that we're given, actually, let's go ahead and pull that up right now, is going to be this type of experimental kind of data. So we're only going to be measuring essentially the nominal values once. So we're going to think about that when we consider precision here. Oh, I don't have permission. Am I able to edit? So you're going to get data like this, which is time on this axis and acceleration in meters squared per second, meters per second squared, excuse me. So this is going to be kind of the data that you're given. So time on this axis, and then you can see kind of the name of this file. LP means length of my beam, L, and the length is equal to point P, 36 meters. And then 2 is just the number of runs. So you'll see that we're changing the length here. So this is, again, time, acceleration. You need to convert that and calculate your discrete Fourier transform. And you have these multiple lengths. So 0.16 meters, 5 runs. 0.36 meters, 5, et cetera, et cetera, et cetera. So you're going to have to analyze all this data set. So when we're thinking about the theoretical values that we've kind of deduced up here, or if we're, because we have to calculate the theoretical frequency and the experimental frequency. So in the theoretical frequency, there's going to be some bias there. Is there going to be some precision here in this calculation? Well, you want to think about that and see if you're given any information here where you could calculate any precision here. If you're given lists, if you're given means, or if it's just measured once. So right here, this is our frequency as a function of these variables. H is the height, nominally 3 millimeters. Y, Young's modulus, 69 gigapascals. Rho, density of the aluminum, 2.71. You might want to be concerned about units here. So make sure to kind of convert where necessary. Length of the beam will vary. I measure the length and the thickness with a ruler that has 1 millimeter tick marks, and the Young modulus will have an uncertainty of at least 5 gigapascals for aluminum 6061, and the uncertainty in my density is 50 kilograms per meter cubed. A hint in terms of how to calculate that, how to convert. So we need the bias error. So we really don't see any precision here in this theoretical calculation because the values are only calculated once. So from that, you can calculate the rest of this total uncertainty for our theoretical calculation. But now let's get into our experimental calculation. So let's look at, I'm going to go ahead, I'm going to pull this out here. I want to look at this data set. So let's look at the data that we have at our disposal. So this is so that's how you calculate your experimental or the theoretical calculations, but you're all experts at that and bias errors. So this is kind of the raw data set again. Time in seconds, acceleration meters per second squared here. I could kind of look at this a little bit nicer here. Let me copy and paste it in. So this is my data. Let's look at how it looks like. That looks like a function or a beam that's kind of, again, varying right here. So you can kind of look at it like that. You can look at it like a list plot. This is definitely, you want to include at least one of this data set. See, it's hard to kind of see with that list line. Although it'd be nice if this was a little smoother function. But anyways, you can kind of see the undulations and kind of the frequencies present in this signal. So we want to now consider and think about, all right, how do we calculate the discrete Fourier transform of this function? Because again, this is, you want to again label this acceleration, this is going to be time, and now we want to figure out, okay, what's the dominant frequency in this signal? So let's go ahead and just gather all of our kind of data as usual. So this is our t data. So if I want my delta t, mean difference is here. I know that my f sub s is this, and then I know my f Nyquist is equal to f sub s divided by 2. So right there. Once I know that, I could get my big N, and I'm excluding the first data point because at t equals 0. I don't want to include that point. And then my period is just this. My delta f will be this, and I can double check that f sub s divided by n, oops, big N. That's the same. And my f Nyquist I know is big N divided by 2 times delta f. Just make sure, 25. Everything's right in this world. So these are kind of the values, and you want to check this for each data set. Because the other thing you want to check is, do you have signal aliasing and spectral leakage in this signal? Well, to do that, we need to calculate the nominal value, basically what's the theoretical frequency. So let's go ahead and let's look at that right now. So let's look at this example. So this example is for a length of 0.36 meters. So if I look at my f equation, so let's look at my sampling frequency first, my f sub s. Fs, so I have that. So this is my f equation. So we know we could supposed to do slash dot here. Y goes to 69 times 10 to the 9. I know that my h, what was that equal to in this experiment, is equal to 3 millimeters. So 3 times 10 to the minus 3. I also know that my rho was equal to 27100. 2710. And then I have my length for this particular value is 0.36 meters. So let's look at, I don't need the arrow, I can just do slash dot. So am I signal aliased here? No, we're good, we're okay. We're good to go. Now, this kind of brings up a question of, okay, well, what frequency resolution do we need? Well, what is our frequency resolution here? It's 0.5 hertz. So we might have a little bit of spectral leakage, but again, it's the question of how much, how do we trust this? Do we trust, how many significant figures do we have here? But the signal aliasing is a really important one. So check for each length if you're signal aliased or not. Could really can help you to explain if there's any data sets that are anomalous. So let's go ahead and calculate our discrete Fourier transform. So these are all my ADAT. Basically, these are my Y values. Here's my A sub n. You're all experts at this now. Here's my B sub n. And then I could plot this. And then if I zoom out, there it is. So here's the dominant frequency here would be about 12.5 hertz. And you could see that's quite different from my experiment or the theoretical value or the nominal value. But I don't know yet if that's, if they're going to overlap or not. I have to calculate my total uncertainties. So that's it. So you have 5 runs. So there's definitely going to be some precision here. Now, bias error. What can contribute to bias error in this problem? it's a pretty complex issue. You can kind of think about what's the resolution of your accelerometer, because that could obviously affect your dominant your kind of the amplitude of your harmonic coefficients. Also, more importantly, what's the kind of precision error in time? Well, luckily this DAC is extremely precise in time. So it's going to be pretty negligible in that component. And similarly for any kind of errors or uncertainty in your accelerometer, that's going to be pretty negligible as well. So you do actually, for this, you do not have to think about basically theoretical error. So it's effectively negligible. So you just have to figure out for experimental precision, for theoretical, your bias error, and that's it. So hopefully a pretty straightforward lab, but again, get into that data analysis, see if they overlap, and if they don't overlap, again, be sure to check for signal analyzing, spectral leakage, and all those other good stuff. So yeah, that's about it. Hopefully pretty straightforward. Good luck, and obviously get started in this early, and let me know if you have any questions. Thanks. Bye.